Okay guys, let's take a look at today's lesson. So what we're going to be doing today is looking at limits algebraically. There are really three main ways to find limits. One would be numerically. We looked at that the last lesson. And really for us, it's like the least used technique. I mean, we do need to know how to do limits numerically, but we just don't use it that often. Then graphically, we learned that last time. That is a very common technique, and also algebraic. The most used are algebraic and graphic. So let's take a look at our algebraic technique. For this one, we have a lot of things going on. First off, we need to look at limit laws. And so limit laws are really helpful to us when the limit is really complex. It allows us to break it apart into little pieces and do them piece by piece. So that's pretty helpful. And there will be some instances where the instructions say that you must use limit laws. So if that happens, my criteria is at least one. You have to use at least one limit law. If you want to use more than that, that's fine, but I need at least one. If the directions say use limit laws, then you have to use them. So let's look at them. What are they? So one is if we were to take the limit of something, we have two functions being added or subtracted from each other. We are allowed to split them apart and take the limit of the first function, then the limit of the second one, and then add or subtract their results. So that's an okay thing to do. If we have a number that's inside here, like 5, and we want to pull that outside the limit, that's perfectly acceptable. We're allowed to do that. Then we would take the limit of the function and then multiply by that number c, whatever it happens to be. Multiplication, we are allowed to split those apart as well. So if we are taking the limit of two functions being multiplied together, we can do them separately and then multiply the results. Same with division. Okay. Also, of course, the denominator can't be 0, but it never can be 0, right? I mean, that's just something we don't deal with. So you are allowed to do that limit law. Another one is a power. If we have a function raised to a power, we're allowed to pull the power, on the outside, take the limit of the function, and then apply the power to whatever number we get. Same with a radical. We can apply that to the answer that we get to that limit. So pretty flexible, kind of nice variety of things that we can do. Alright, so now let's look at strategies for finding limits algebraically. What are we going to do? Well, the very first thing that we're going to do is we're going to plug this number in, a, whatever it is. We're going to plug it in and see what happens. Okay, if we get 0 over 0, that is called an indeterminate form. If we get that indeterminate form, then what we're going to do is we're going to keep going. 0 over 0 means keep going. It does not mean 0 necessarily. I mean, I guess it could be 0, but then it could be -1. I mean, we don't know what it is. That's why it's called an indeterminate form. We can't determine what it is without more investigation. And so we plug the number in. We get 0 over 0. That means keep going. So we would need to use algebra or trig to rewrite it, to make it look different, to simplify it. We have to do something. Some techniques that you might try are factoring and reducing, multiplying by the conjugate, finding a common denominator. Those are just some of the algebraic techniques that you might try. Our other option, and I'm going to add a word in here, if plugging in a number results in the denominator being 0, and the denominator only being 0, not this situation. This situation means keep going. Okay, do something algebraic. Do algebra. That's what that means. 0 over 0 means keep going. Do something. If I get like 2 over 0 or 10 over 0, if I get just a 0 in the denominator only, then I'm required to do the right and the left-handed limits. Okay, and we're going to do a couple of examples of this because for some students this is the more difficult one. They're like, what is that? And we're going to do a couple of examples of this. Okay, so those are our options. We get 0 over 0, we keep going. If we get like 2 over 0, we do the right and the left-handed limit. Okay, so that's our technique. So let's look at a few examples on the next page. Okay, so on this first one, go ahead and add in, I should have put in the instructions, use limit laws, just for number 1. Use limit laws. 2. You only have to use limit laws when that's in the instructions. And for my students that like to conserve energy, if it's in the instructions, you must use at least one limit law. Okay? If it's not in the instructions, then you don't have to. But we're going to, for this first one, this is a perfect example of when you would be asked to use a limit law. We're given this information just in abstract. We don't even know what f of x is. We do know that the limit as x approaches 3 of f of x is 2. We have no idea what the function is. Same with g of x. We don't know anything about it except that the limit as x approaches 3 of g of x is 0. So this would be a perfect opportunity to use limit laws since we have no idea what else is going on. So we're going to use a minimum of 1 limit law per problem, which will be pretty straightforward. So we'll start with this one. These are 2 functions being added together. We're going to split them apart using that first limit law. The limit as x approaches 3 of f of x plus the limit as x approaches 3 of g of x. Okay, so there I've used the limit law. Yay. Okay. Now what I'm going to do is I'm going to use substitution. I'm going to replace limit as x approaches 3 of f of x with 2. And I'm going to replace limit as x approaches 3 of g of x with 0. And so my answer for this first one is 2. Okay. All right, let's take a look at part B. So we're going to use a limit law. We're going to break this apart. So the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x. Okay, there's my limit law. Now let's substitute. Let's put the values in. All right, so we're going, let's see, that would be, we substitute a 2 in there divided by 0. Okay, that's a problem, right? That's a problem. So we are going to say it's D and E, but we're never allowed to just write D and E, right? Never allowed to just write D and E. We have to say why. Normally what we would do, this is like that instance on the other page when we have 2 over 0, we would investigate. We would do the left-sided limit and the right-sided limit. We would see what's going on. But we don't even know what f and g are. We can't do the right and the left-sided limit. We're kind of stuck here. We really can only say what we know, and that is it's D and E because it's undefined. And that's all we know at this point. So the reason that this one is D and E is because it's undefined. Okay? Now part C, I see students all the time write the answer to this in a very strange way. They say they don't do any kind of work. They just say the answer is x squared times 2. Okay, that's not the answer. Okay, it's not the answer. It's not x squared times 2. We're going to use limit laws and we're going to break it apart, so hopefully we will see better what to do. These are 2 functions being multiplied together. We actually know what this function happens to be, which is nice. We don't know what this one is, but that's fine. Okay, we're still going to break them apart. So the limit as x approaches 3 of x squared times the limit as x approaches 3 of f of x. Okay, so let's deal with these separately. This is a regular algebraic limit. What do? I just plug in the 3, right? That's just a regular algebraic limit. So I plug in the 3 and I get 3 squared times. This one is one that we were given, right? This one we were given this up here. So we're going to use substitution and we're going to put a 2 in its place. And so my answer is actually 9 times 2 or 18. It is not x squared 2 times 2, right? Because we can take that limit. Questions on that? So that's how we would use limit laws. Okay? All right. So the rest of these are just regular algebraic ones. You can use limit laws if you want to. You don't have to. It's totally up to you, however it works out. But what we are going to do the same thing every time. We're going to plug in the number. Okay, so I'm going to plug in a 1. I plug in a 1 here and I get, what, negative 4 over 0. Okay. So that's like on the last page, that bottom thing. If you get a 0 in the denominator only, this is what you're going to do. you're going to do you're going to do the left side and the right side limit. That's what you're going to do. So I'm going to stop here, and I'm going to draw arrows. So this is going to be the limit as x goes to 1 from the left of f, and we're going to do the limit as x goes to 1 from the right of f. And so I would like to kind of whittle down what f is. This right here is f, but I would prefer to deal with it in a more simplified form. I think if I factor, I could probably cross some things out, right? Because I would rather deal, with something smaller. This is a bit too big for me, so I'm going to go ahead and factor. I'm just going to factor right over here on the problem. So this is what, an x minus 3 and an x plus 1, and then the denominator, that's an x minus 1, x plus 1, right? And so we would cancel those out. So I'm going to say that f is x minus 3 over x minus 1. That's what I'm using as f. I'm using the simplified version, which is perfectly fine. Okay, so the technique that I do with these, I do the same technique every time. It's never failed me. When I am not sure what to do, I default to numeric. That's just what I do, graphic or numeric. When I'm not sure what to do algebraically, either if it's easy to graph, I graph it. If it's like this, I'm going to do it numerically. And when I have the situation, it's when I have this, a number over 0. I do the same thing every time. All right, I'm going to go 1/10 on either side of 1. So coming from the left, I am going to, and I'll just put it under here, I'm going to plug a 0.9 in to f and see what I get. I don't really only care about the signs, because what this is an indication of, it's an indication of a vertical asymptote. That's what this is an indication of when we have a fraction like this. Okay, there's a vertical asymptote there. And so I'm going to go 0.9, so that's 1/10 to the left. If I put a 0.9 in the numerator, I'm going to get a negative number, right? If I put a 0.9 in the denominator, I'm going to get a negative number. And that tells me that I'm going to positive infinity. So graphically, what this would look like is I'm coming from the left, I'm headed this way to positive infinity. Okay, there's an asymptote here. Okay, so now I'm going to focus on coming from the right. When I'm coming from the right, I'm going to use 1.1 and I'm going to plug that in and see what I get. Alright, so I put a 1.1 in here, and that gives me a negative number. Right? I don't really care what the number is, it's just negative. If I put a 1.1 down here, I get a positive number. So what does that mean? That means I'm going to negative infinity. So if I look at the graph, graphically, I'm going to be headed this way. Okay? So what I'm getting to with these number over zeros, it's not acceptable just to write a D and E. Like if we had one like this on the AP test next year, they would say, positive or negative infinity. They would say something. Or they wouldn't just say D and E, I'm done. Right? They would say something. So in this case, because we're headed different places on either side, this one is going to be a D and E. And because I can just write to my work, I don't have to rewrite it. I just showed someone that coming from the left to the right, I have a different value. Right? That's the usual answer for D and E, is the left and the right sided limit don't match. Okay, so my answer is D and E, and my because is this work right here. If you really are troubled and you don't want to just leave it like that, you could say, because the limit as x approaches 1 from the left of f does not equal the limit as x approaches 1 from the right of f. Okay, this is the formal reason why that's a D and E, because they don't equal each other. We okay with that? Okay, we have one more like that, because this one, for whatever reason, really troubles students. So I'm going to put a 2 in here. I put a 2 in here and I get negative 2 over 0. Okay, what does that mean we have to do? The two one-sided limits, right? We should say, what does that mean we get to do? We get to do 2 limits instead of 1. It's like double the fun, right? Yay, 2 limits. All right, so we're going to do 2 limits. We're going to do the limit as x goes to 2 from the left of f, and we're going to do the limit as x goes to 2 from the right of f. Okay, that's what we're looking at. Now, 2 from the left, I'm going to use 1.9. That's just what I do. It has never failed me yet. Just 1/10 away is close enough. Could you get closer if you wanted to? Sure, you could go, 1.99 if you wanted to. I mean, you can get as close as you want, but for me, a 1/10 has always been sufficient. So I put a 1/10 in here. Excuse me, we're going to go back here. We're going to put 1.9 in here. Well, first of all, the numerator is negative, right? I can't change that. It's just a -2. The denominator, I put a 1.9 minus 2. That's a negative number. But what happens when I square a negative number? I get a positive number. So this side is going to negative infinity. Okay? So coming from the right, I'm going to use a 2.1. And you don't have to write these numbers down here. I'm just showing you what I'm doing. Right? I'm just demonstrating what am I doing. I'm using, I go 1/10 on either side. So let's look at the graph. So what would this look like? I have it 2. So coming from the left, we're headed to negative infinity. Okay. Coming from the right, let's investigate that. What do we have going on? Well, there's a negative in the numerator. Right, can't change that. So 2.1, that gives me a positive, and a positive square is a positive. And so that takes me to negative infinity. So my answer to this is negative infinity. I'm headed both ways. I mean, from either side, I'm going to negative infinity, so that's what I would write. Okay, how are we with the ones where it's a number over 0? We okay? Because that's what we're going to do every time. It's not going to change. Every time. 2 limits, go a 1/10 on either side. You got it. All right, so now let's look at some other types. Let's look at this one. If I plug a 0 in, let's see, root 3 minus root 3 is 0. I get 0 over 0. 0 over 0 means keep going. Do something algebraic. Do something. All right, so we look at it and we think, well, what could we do? What could we do? And I want you to remember, you may not remember, but you can only multiply by the number 1. You can't square anything. You can't multiply by anything but 1. That's it. Okay? That's all we got. So when we have something that looks like this, the best technique to start with or to try would be to multiply by the conjugate. That would really be the best thing to do. So we're going to rewrite limit as x goes to 0. So we have root x plus 3 minus root 3 over x. So remember, the conjugate is the same as this, but the middle sign is different, right? So it'd be square root of x plus 3 plus root 3. And we can only multiply by 1. Square root of x plus 3 plus root 3. Now, resist the temptation to distribute the non-conjugate part. Resist. I know we want to. We want to distribute this x. Don't do it. Because if you do, you could miss the magic that's going to happen, right? Because there's going to be some magic that's going to happen when we multiply by the conjugate. It's just going to because we started with 0 over 0. That means there is an answer. It's like buried treasure. We just have to kind of go and find the little buried treasure. What is it going to be? I don't know. All right, so don't distribute the x. Just distribute the conjugate part. Just do this part. So let's do that. So limit x goes to 0. We know root x plus 3 times root x plus 3 is just x plus 3. And the beauty about the conjugate is the outside and inside go away, right? Outside and inside go away. Then I have negative root 3 times a positive root 3 is just minus 3. Minus 3. Okay. Come on, gosh. Okay. So it's a minus 3 over, okay, don't distribute. Leave the x separate. X times root x plus 3 plus root 3. Okay. So let's clean it up a bit. In the numerator, we see that 3 minus 3, we're left with an x. So let's just, and notice, I want you to notice how I'm carrying the limit with me. See that? See my little friend right here? It keeps coming along with me. We don't leave it behind. How rude. Do not leave it behind because it would hurt its feelings. Plus, we wouldn't even know what we were doing. Why are you writing all that stuff down? I mean, I don't know. Is it a limit? Well, I don't see a limit, so we need to keep it there. So x over x times x plus 3. Wow, and see the magic right there. If we had distributed it, we might have missed it. I can't tell you how many students who have distributed miss it, and they're like, I don't know what to do. I don't know what to do. Well, okay, don't distribute, okay? Don't distribute on the non-conjugate part, and then you'll know what to do. Now we're ready to take the limit. So 1 over, I put a 0 in here. 0 plus 3 is 3, so root 3 plus root 3. Is there a more simple way that I could write that? Sure, right? 1 root 3 plus 1 root 3 would be 2 root 3. So my answer is 1 over 2 root 3. See, so this time 0 over 0 was actually 1 over 2 root 3. Okay, how are we? We all right? Okay, last one. All right, so let's plug in a negative 3. Let's see, I have 1 over negative 3 minus 1. That's 1 over negative 4. So that's 0 over 0. We know what that means. Keep going, right? There's a present hidden in there. Now this, hopefully we know this is kind of a mess, right? I mean, it's a complex fraction, you know. So the thing that I would think to do is to fix the complex fraction, right? That's what I would do. So that's what we're going to do. So let's fix the complex fraction. Limit x goes to negative 3. So my common denominator would be, what, 4 times x minus 1? So I have 4 over 4 times x minus 1 plus, plus x minus 1 so we get x minus 1 over 4 times x minus 1 all over x plus 3. Okay, is that okay? So let's add those fractions together. Limit x goes to negative 3. So let's see. So we have 4 plus x minus 1 over 4 times x minus 1 all over x plus 3 over 1. Okay. Is everybody okay? All right, let's keep going. So the limit is x goes to negative 3. All right. So here, that's what, 3 plus x, right? And this is a complex fraction that I want to fix. Instead of dividing them, I want to, do the reciprocal and multiply. So this is going to be 3 plus x over 4 times x minus 1 times, we're going to take this and flip it upside down. So 1 over x plus 3. Okay, we're not distributing, right? Because we may miss the magic. Do you see what we can cross out? Yes, because that's always going to happen because it's 0 over 0, right? There we go. It's gone. So now I'm ready to take the limit. So I have 1 in the numerator over. I put a negative 3 here. So 4 times negative 3 minus 1 is negative 4. Or negative 1 over 16. This time 0 over 0 was negative 1/16. Okay, are we okay? All good? All right.